All right, Ivan, are we good to go?
Yes.
Awesome. All right, good morning, everybody. I hope you're having a great day, whether you're in Marcus or live streaming in. We are continuing with our work in section 4.1. So as a reminder, there was no mini quiz yesterday, but there will be one on Sunday. So make sure that you log in to complete that. So as a reminder, what we're working on is identifying local maximums and minimums by using what we know about the first derivative. So I'm going to go ahead and switch over to the DocCam. Okay, so where we landed at the end of last class and where we're going to pick up today is using this test for critical points. So we said last class we spent a lot of time finding critical points for a lot of different functions. And we said, okay, now that we know how to find where they are, how do we determine if they are local maximums, local minimums, or neither? And so our first test that we were employing was the original function test, where we are visually inspecting if we have a graph. We will look at where the function's increasing and then decreasing, which gives us a local maximum, or decreasing and then increasing, which would give us a local minimum. Or if we don't have a graph, using these same ideas to evaluate what we do know. And so we went ahead and we did a couple of graphs on some of the things we had looked at before. And that's where we are going to pick up today. So we're still sort of building on the stuff that we had been working on. And so where we're going to begin is we are going to think about how we can use the graph of the two more complicated functions we worked on last time to help us classify our points. So as a reminder, for example, 3, we used the quotient rule. And then we did some simplification, and our first derivative was x squared minus 4x, all divided by x minus 2 squared. From that, we were able to determine critical points of 0, 2, and 4. We set the numerator equal to 0 to find the points where the first derivative equals 0, and we set the denominator equal to 0 to find any points that were undefined. So that's where we got our critical points. And so now what we want to do is we want to graph this function, the x squared divided by x minus 2, so we can look at 0 and at 2 and at 4 to try to see what's going on. So we can visually look at and determine, are these local maxes, mins, or neither? And then we're going to do the same thing with our product rule function. We had x cubed times 1 minus x to the 4th. We did a product rule. We did some factoring. We were able to factor it so that we could find our critical points, and we had 0, 3/7, and 1. And so now we want to know, are those local maxes, mins, or neither? So we will have to graph the original function and look at 0, 3/7, and 1 to see if we can determine visually if they are maxes, mins, or neither. Okay, so I want you to try that. We're sort of wrapping up this first test just by practicing our graphing. So I'm going to give you about 3 minutes, see if you can get those graphed. And if you can get those graphed, look at these values to see if you can figure out what they might be. Okay, so try that out, and then we will go through that together, like I said, in about 3 minutes. Okay, take about 30 more seconds. Okay. So I'm going to do my best to graph example 3 by hand, and then I have example 4 graphed on my calculator because I want to talk a little bit about that. So let's start with example 3. So when we graph this, you may have to zoom around either in or out, left or right, reset the window, because when you have things that are quotients or a little more complicated than a simple polynomial, the graphs tend to do really interesting things. So this one, if you zoom in enough, what you find is that it looks something like this to the left. So this is 2, 3, 4, and then up here, here's something that comes down and goes up. So we get something that looks like this. And so what we need to do when we have a picture that looks like this is we need to go to each of our critical points and see what's happening. So when we go to 0, right, we're really hyperfixating on this point right here and what's happening in this area. So at 0, we see our function is increasing and then decreasing, right? It's going up and then down. So right at 0, we see we have a local maximum. Okay. And then when we go to 2, what we notice is that at 2, we have this asymptote, right? We don't have a local max or a min. We have this discontinuity. And so visually, that tells us that this is neither, right? We don't come to a maximum or a minimum in any meaningful way here. And then when we go to 4, right, we come over here. We have 4 here. We look at sort of this general small area. We see we were decreasing and then increasing around 4. So that gives us a local minimum. So we are using this picture and this idea of increasing, decreasing to help us classify these critical points. We are going to classify these same critical points for the same function with another test later, and we'll see that it agrees. No matter which test you use, you're going to get the same answers because they are the same critical points. So that's how we might use that particular graph. Now, when we do example 4, I did this on my calculator, and I kind of want to show you what that looks like for me. So I entered the function, and I spent a lot of time playing with the window. So in order for me to actually be able to see these critical points and what they were doing, what I ended up needing to do was having my x values be between -1 and 2 on my graph. So as a reminder, the critical points were 0, 3/7, and 1. So those all fall between -1 and 2. But then my y scale, I needed to zoom in very, very close. If I didn't zoom in, it just looked like a weird flat line everywhere. So I had to zoom in to -0.1 to 0.1. That's how close I needed to be to get my graph to even look like anything. And so when I graph it and I'm zoomed in that far, this is the picture I see. And what I want to note here is if you are spending a lot of time trying to see the graph, it may not be the best test to use. We're going to learn the 2 other tests today. So one of the other tests might be more practical if the graph is really complicated. So what I notice here when I'm thinking about this particular graph is that for x equals 0, I see that my function is increasing, and then we're at 0, and then we're increasing again. So it doesn't turn around to create any sort of nice, easy to identify local max or min. So I think that x equals 0 is going to be a case of neither, okay? Because again, the rules say you have to go from increasing to decreasing or decreasing to increasing. Now at 3/7, what I'm seeing here is that I'm increasing and then decreasing, right? And I know this is the 3/7 because this little tick mark is my 1. So this is between 0 and 1. So this is creating a local maximum at 3/7. And then finally, looking at what's happening at 1, I see that, as I move away from 3/7, I'm decreasing and then increasing. I see that this makes like this little U shape. It's subtle and a little flat, but I'm feeling pretty confident that that is a local minimum. Okay, so again, for me anyway, I probably would not choose to use a graph to classify this particular function just because it is so finicky. I would use one of the other tests that we'll learn today, but you do have options, okay? So that's the 2 last examples on the algebraic type of classifying critical points using the original function. I want to do one more example that is not algebraic, okay, where we have a table. And so I want you to think about how we might be able to apply what we know about this idea of increasing and decreasing to the table given the information in the problem. So what we're told is that f of x and f prime of x are continuous functions that are differentiable. So since they're continuous, we are not worried about any weird asymptotes or holes or jumps or anything like that. We also know that f of x has a critical point at 5 and at 11, okay? And we want to use this table of values of f of x to figure out if these critical points at 5 and 11 are likely to be local maximums or local minimums, okay? So I want you to take a minute, see if you can think about how we can apply this test to this table for 5 and 11, and jot down your thoughts on that, and then we'll go through it together in just a minute and a half. Okay, so we want to mark where our critical points are. So we know that they're going to happen at x equals 5 and x equals 11. But what we see on this chart is that 5 and 11 are not points that are labeled. So we kind of have to put them in roughly where they will be, right? So 5 will be between 4 and 6, and then 11 will be between 10 and 12. And we know from our test that we're interested in whether the function is increasing and then decreasing or decreasing and then increasing. So the way that we would determine that from a table is to look at the y values and see, are they going up or are they going down? So here we have 4 and then 8 and then 10. So these values are increasing. Then we have 8 and then 5 and then 2. So as we move from left to right, these are decreasing. And then 7 to 10, we are increasing again. Okay, so what our test says is that if your function is increasing and then decreasing around a critical point, which is what we're looking at here, we're going up and then down, it makes that critical point a local maximum. Right? Because again, if you are increasing and then decreasing, the shape looks like this. For our second critical point, we are decreasing and then increasing. So that's going to make us a local minimum. So when we have information about the original function, we can use that in conjunction with that first test, the original function test, to classify our critical points. So that's how we would work through that, okay? Excuse me. So we are going to move on to our next test, and this is classifying critical points part 2. So this means we're going to be using a different method to determine if our critical points are local maximums, local minimums, or neither. So we're going to be working with the same functions. So we already know the outcome, but we're practicing the tests, okay? So we're going to start with this function that we were working with at the beginning of classifying critical points part 1. And again, whenever you have any sort of algebraic function, in order to classify the critical points, the first step is always to find the critical points. We did this last time, but I'm quickly going to go through it again, just as a reminder. When we're looking for critical points, we're starting with the first derivative, which here will be 12x squared minus 12x minus 72. We want to know, when does that equal 0? We have to factor this. So we end up with x minus 3, x plus 2 equals 0. And we get our critical points at x equals 3 and x equals -2. Okay, so when we are doing algebraic problems, the first step is always to find the critical points. And then once you've identified them, then you are going to decide which test is appropriate to classify them. So this is going to be our first step always, is to find these critical points. Okay, so I'm going to write this again on the next page for us here. So we said that our critical points, well, our first derivative factored out, because we're going to use the factored version, was x minus 3, x plus 2, and our critical points were x equals 3 and x equals -2. Okay, I'm just copying that over from the last page. So what we want to do now, when we use this particular test, which again is a new test that we're trying out, so we haven't done this yet, is we are going to use our critical points to divide the domain of the original function into intervals in which the sign of the first derivative remains the same for that entire interval. What in the world does that mean? Okay, what that means is that the critical points are when the function changes from increasing to decreasing or decreasing to increasing. And between the critical points, it will be doing the same thing, because if it wasn't doing the same thing, we would get more critical points. Okay, so the way that this test works is that we are going to create a number line for the first derivative. Okay, and the number line, we are going to put our critical points on the number line in increasing order, like you would label any number line. So we have -2 and we have +3. Okay, and what we know so far is that at those points, the first derivative equals 0. Okay, so what this is saying is that this is going to create intervals in which the original function is doing the same thing. So what are these intervals? So this one is -∞ to -2. That's the first interval. Then we have -2 to 3. It's the middle interval. And then we have 3 to infinity. Okay, the critical points divide up our interval in which the interval does the same thing. So whatever is happening between -2 and 3 doesn't change. So if it's increasing, it's always increasing between -2 and 3. If it's always decreasing, right, then it's the same. It doesn't change on the interval. So what do we want to do with this information? Well, we're going to tie this back to what we learned in chapter 2 about the relationship of the sign of the first derivative and what the original function is doing. What does that mean? So as a reminder, if the first derivative is positive, the original function is increasing. If the first derivative is negative, the original function is decreasing. So we are going to work to find the sign of the first derivative for each interval, because that will help us know whether or not these critical points are local maxes or mins. Okay, so how does this work? So we are going to pick a test point. okay, on each of our 3 intervals. So here to the left of -2, I need to pick a value smaller than -2. You can pick any number between -infinity and -2, but you really want to pick one that's going to be convenient and easy to work with. So I'm going to pick -3, right? I'm unlikely to pick -1 million just because that's, not as easy to work with as -3. And what I want to do is I want to determine, is the first derivative positive or negative at -3? Because the sign at -3 will be the sign for the entire interval. There's 2 ways you can do this. You can take the unfactored form of your first derivative and plug in -3 and use your calculator. That's totally fine. The way that I do this is I just look at the factors. So for me, this is my factored form of the first derivative. 12, always positive. Okay, if I were to plug a -3 into my first factor here, -3 minus 3, it's going to give me -6. So that's something negative. And then if I plug in a -3 plus 2, I get -1. That's negative. So if I do positive times negative, the negatives cancel. And I know that this interval is positive on the first derivative. So what does that tell me? If the first derivative is positive, then the original function is going to be increasing on that interval. Okay. Now, the next interval is -2 to +3. So I'm going to pick a number between -2 and +3. I'm going to pick 0, right? 0 and 1 are easy things to work with. And I'm going to do the same thing. I'm going to take my 0. I'm going to come up here and I'm going to figure out if the first derivative is positive or negative. So 12 is always positive. 0 minus 3 is -3, so negative. 0 plus 2 is +2, so that's positive. So positive times negative times positive is negative, right? So that tells me that the original function, right, must be decreasing on this interval because the derivative is negative. And then finally, I'm going to test something slightly bigger than 3. So I'm going to pick 4. Again, you can pick any number between 3 and infinity, but pick one that's easy and convenient to work with. I come up here, 12 is always positive. 4 minus 3 is +1. 4 plus 2 is +6. Positive times positive times positive gives me something that is positive. If my first derivative is positive, that tells me that my original function is increasing. So how does that help me classify my critical points? Well, if my original function goes from increasing to decreasing, I know that that creates that hill that makes -2 a local maximum. Okay. So this is a local max. And if my function goes from decreasing to increasing around my critical point of 3, that means I'm going down and then up. That makes a local minimum. Okay, so I'm able to determine what these critical points are by looking at how the first derivative changes. Okay. And so because those sign changes relate directly to the original function, I can create a set of rules for this test to help me understand when I have local maxes and mins. So if the first derivative changes from positive to negative around your critical point, positive to negative, then that critical point is a local maximum. And again, the reason is because we're going increasing and then decreasing on the original function. If your first derivative changes from negative to positive around your critical point, then your critical point is a local minimum. So negative to positive means decreasing to increasing. That creates a minimum. If your derivative does not change around your critical point, then it's neither. So if this was positive to positive or negative to negative, that would mean neither. Okay, so if it doesn't change, then you don't have a local max or a local min. Okay, So we're going to practice this idea of using these number lines with the first derivative to find the signs and then pair them with this test to determine if our critical points are maxes and mins. So again, we're going to work through the examples that we've already done. So we've already found the critical points for these particular functions, and we graphed them last time. So we already know what to expect, but we're really practicing the test. So we're going to start with the two algebraic functions. Okay, so the first one is 3x squared plus 6x plus 1. We want to use this first derivative test to classify our critical point. So as a reminder, we found the first derivative and then set that equal to 0. That's how we got that critical point. There's one critical point at x equals -1. So we're going to set up a number line for the first derivative here, and the point we're going to put on it is -1. So we'll have to test something to the left and to the right to see how it changes. For example, 2, again, we had 2x cubed minus 3x squared minus 36x plus 14. We found the first derivative. We factored it. We used that to find our critical points. We got 3 and -2. So again, we are now going to set up a number line where we're going to put -2 and 3 on our number line, which is going to create those intervals. We're going to find the sign of each of those intervals, and that's going to allow us to classify those critical points. So I want you to try these two problems, setting up these number lines and getting comfortable plugging things into the derivative. I'm going to give you about 3.5 minutes to do both of them, and try your best to just work through, get comfortable with plugging things into the derivative, and then you can use these classifications to see how it's changing. So if your derivative goes from positive to negative, it's a max, negative to positive, it's a min. But classify these 3 critical points, and then we will go through it together. So give it a try. Okay, take about 30 more seconds. So for example 1, we are lining up our number line and putting our critical point right on the number line. We know that the derivative equals 0 at -1. That's what makes it a critical point. Okay, so that creates 2 intervals for us, the interval from -infinity to -1, and the interval from -1 to positive infinity. And so we want to know the sign of the first derivative on these 2 intervals. So we're going to pick something slightly to the left of -1 to test. So I'm going to pick -2. Again, you can pick any number to the left here. So when I plug a -2 into my first derivative, I have 6 times -2, which is -12, plus 6 gives me -6. The 6 isn't important, the negative is. Okay. So then I also want to test something to the right of -1. So I'm going to pick 0. You could pick 1, you could pick 2, anything over here to the right. When I plug this in here, 6 times 0 is 0, plus 6 gives me +6. So here, I see that my function was decreasing and then increasing. If I check my rules, here I'm going from negative to positive, because I read this from left to right around my critical point. So if I go from negative to positive, that gives me a local minimum. And remember, the local minimum is at the critical point that we have put on to the number line. Okay, so x equals -1 is a local minimum. And that agrees with our graph. If you remember what the graph looked like, you may or may not, that was last class, but it looked like this. Okay, and so we found it was a local minimum because we could see the U shape over here at -1. So again, no matter which test you use, you will get the same result. So it's not, you should never get a conflicting result. All right, example 2, again, we're going to draw on our number line. We're going to label our critical points. So we have -2, we have +3. We know that they are 0 right at those points. And now we want to do some test points. So if we do something like -3, we can plug that in here. We have something positive. -3 minus 3 will be negative. -3 plus 2 will be negative. So we have positive times negative times negative. That's going to give me something positive. I'm going to test something between -2 and 3. I'll test 1. So 6 is positive. 1 minus 3 is -2. That's negative. 1 plus 2, that's positive. Positive times negative times positive gives me something negative. And then something slightly bigger than 3, like 4. 6 will be positive. 4 minus 3, positive. 4 plus 2 is positive. And again, if you don't like this type of analysis, you can literally plug it into the first derivative on your calculator and look at the sign. It's the same thing, right? So you can plug a 4 in here, 6 times 4 squared minus 6 times 4 minus 36, right into your calculator, and you should get something that's positive. Okay, same idea. So again, we're looking at how these change. Since we are going from positive to negative, that's going to make our critical point of -2 a local maximum. And then here we're going from negative to positive. If our first derivative goes from negative to positive, it makes your critical point a local minimum. Okay, so again, when we use this type of test, we are looking for the sign change. That's sort of the crux of this second test. And so we're going to do a couple more of these, but I do want to point out, when you have an original function, I often think it's a good idea to both graph it and use one of the other 2 tests, right? So, for example, here we have the picture. The picture looks like a minimum. And then if I also do this test, it confirms it, right? I didn't mess anything up in plugging in. Sometimes, however, you only have information about the first derivative. And if that's the case, you have to use this type of test. And we'll look at some of that later. But for now, let's keep going with our number lines. So the other two examples we have, these ones are a little more algebraically challenging, and using the classification doesn't change that. So when we have these problems, we have x squared over x minus 2, and then x cubed times x, or 1 minus x to the fourth. We found our first derivative for each of these, and we found our critical points, but now we need to classify them. So when we do these number lines, we have to be a little more careful plugging in to determine if things are positive or negative. Okay, so just do your best to be careful about that, but I want you to try it with these types of functions. Again, you know, you want to draw your number line, you want to label the critical points, create your intervals. You want to do a test point on each interval by plugging into the first derivative and determining if it's positive, negative, or 0. I will say that for the second one, it might be helpful for you to turn 3/7 into a decimal on your calculator, so that when you're picking something between 0 and 3/7, you know, that you find something actually between them. Or you could pick something like 1/7 and 5/7, right? If you want to keep the fractions, that's fine too. So try these out, draw your number lines, label the critical points, see what you can figure out. Again, we found these derivatives last class, so if you want to look back to that and see how we found those, that's totally fine. But we got them by setting our first derivatives equal to 0. So again, I'm going to give you about 3 minutes to do these two problems. They're not more difficult, you just have to do them more carefully with your plugging in. Okay, so try that out, see what you get. If you finish before the 3 minutes is up, you can compare that to the first two problems we did today, where we graphed these two, and make sure that what you found here is the same as what we figured out from the graph. Okay, so try that out, and then we'll go through it together. And like I said, about 3 minutes. Okay, take about 30 more seconds. All right. So in this particular case, we have 3 critical points, which means we have 1, 2, 3, 4 intervals that we need to test. So for each of these, I'm going to be picking a test point to plug into the first derivative. So I want to take a minute to look at the first derivative and notice if there's anything helpful that will make this a little bit easier. So here I have x squared minus 4x over x minus 2 squared. Since the bottom is squared, it will always be positive. Okay, so remember that one of our critical points is 2, so we don't need to worry about that. We know that that's a critical point and that we're undefined there. So we can actually put a U here for undefined. But when we do our test points, the denominator is always going to be positive because it's squared, which means that I can just use my test point in the numerator to figure out the sign. Okay, so I need to pick something to the left of 0. So I'm going to pick -1. So if I plug in a -1 into the numerator, I get -1 squared. So I have 1, and then I end up with +4, right? Because I have a -4 times -1. So 1 plus 4 gives me +5. So I get a positive value in my little first test interval. Now I want to test something between 0 and 2. So I'm going to pick 1, just because it's a convenient number. So when I plug a 1 into the numerator, I get 1 minus 4, which is -3. So that's going to be negative. And again, I'm ignoring the denominator because it's always going to be something positive. If you're plugging it all the way in, that's totally fine. You should get the same answer. So between 2 and 4, I'm going to pick 3. So again, 3 squared is 9. Minus 12. 4 times 3 is 12. 9 minus 12 is going to give me -3. And then I have to pick something slightly bigger than 4. So I'm going to pick 5. 5 squared is 25. And so I have 25 minus 20 when I plug in a 5 here, which gives me +5. So now I have all my intervals and I'm interested in how they are changing. Okay. So when my interval changes from positive to negative, that gives me a local maximum. So my critical point of 0 is a local maximum. Okay. Here, I have negative to negative. That did not change. If it does not change, that's neither. And if you looked back at our graph, that's where we had that asymptote. Okay, so that agrees with what we were doing before. And then if we go from negative to positive, that makes our critical point a local minimum. Okay, and this agrees with the picture that we did in the first problem we looked at in terms of classification. So just as a reminder, this is what the picture looked like for the original function. We had this graph here, where we had a maximum at 0, a minimum at 4, and neither at 2. And that's what we're finding here with this same test, right? With this other test. So it confirms what we found before. Okay, so let's go ahead and look at example 4. So we have our function and we have the derivative, and now we need to set up our number line. So our points here that we're testing, we have 0, we have 3/7, and we have 1. So again, we end up with 4 intervals that we need to test. Okay, so we're going to try to pick our points carefully just to be easy. If you picked your points differently, that's totally fine. When we have teeny tiny fractions, you just have to be extra careful. Okay, so when we pick something to the left of 0, I'm going to pick -1. I think that'll be the easiest to work with. And again, you can plug this into your calculator with a -1. I like to just go term by term like I did before. So -1 squared is going to be positive. 1 minus -1 is +2. +2 cubed gives me +8. That's positive. And if I plug in a -1 here, I get 3 plus 7 because of the -1, which is 10. So that's positive. So positive times positive times positive means my interval over here is going to be something positive. Okay. Now I'm going to pick something between 0 and 3/7. There's a couple different ways you can pick a number this way. If you prefer to work with decimals, that's fine. You can turn this into a decimal and pick a decimal. I like to work with fractions, so I'm going to keep mine as a fraction. But again, as long as you pick any number between 0 and 3/7, we should get the same result. So I'm going to pick 1/7. 1/7 is less than 3/7. So 1/7 squared is positive. 1 minus 1/7 is positive, so that cube will also be positive. And then for my last parenthesis here, 3 minus 7 times 1/7. Okay, so 7 times 1/7 is 1. 3 minus 1 is 2. So that's positive. So I have positive times positive times positive, and I get something positive. Now I need to pick something between 3/7 and 1. So I'm going to pick 5/7, right? 5/7 is bigger than 3/7. So 5/7 squared is positive. 1 minus 5/7 is 2/7. 2/7 cubed is positive. And then here, I have to think about what 7 times 5/7 is. 7 times 5/7 is 5. So 3 minus 5 is negative. So I have positive times negative. So that's going to give me something negative. And then I'm going to pick something bigger than 1. So I'm going to pick 2. 2 squared is positive. 1 minus 2 is -1. -1 cubed is negative, right? Because it's to an odd power. And then here, if I plug in a 2, I get 3 minus 14. 3 minus 14 is also negative. So I have positive times negative times negative. The negatives will cancel, and that will be positive. Okay, so now I can look at how things change or not to determine and classify my critical points. So at 0, it's positive to positive. If it doesn't change, that critical point is neither. And if you remember, that was like the weird flat spot that I said was probably neither, and now we've confirmed that. When we go from positive to negative, right, that means we're going to have a local maximum at 3/7. And then here, if we go from negative to positive around a critical point, that means we have a local minimum. Okay, and so we have neither at 0, a local max at 3/7, and a local min at 1. And as a reminder, this is the one I did on my calculator, so I'm just going to show you the graph one more time. That agrees with what we said before. 0 is neither because it's increasing before and after 0. We have this little local max at 3/7, and then we have this local min at 1. So that agrees with our picture. So again, you know, if you are able to do one of the tests and graph it and they agree, that's pretty solid evidence. One thing I do want to mention is that since we're using these test points and we have a lot of numbers floating around, it's really important to remember what your critical points are that you are classifying, so that when you get to the final conclusion, we're saying 3/7 is a local maximum. You know, x equals 1 is a local minimum. These other numbers on the line were just test points to help us understand, right? So keep in mind what are the actual critical points, okay? So this is how we use this test algebraically. We are really interested in how the first derivative changes signs, right? From positive to negative or negative to positive. We can also do this with some of the other types of functions we looked at when we talked about critical points. So let's go ahead and see how else this might come up. So Suppose that f prime of x is given in the graph below. Use the graph to determine where f of x has a local maximum or minimum on the interval. So when we saw this graph the first time, we were trying to find the critical points. So as a reminder, since this is a graph of the derivative, the critical points are where the derivative equals 0, right? And we said that that's where it crosses through the x-axis. And now that we know where the critical points are, we want to use this classification test to determine if those critical points are local maximums or minimums of the original function. So we're thinking about how the first derivative changes sign. So I'd like you to take a minute. I'd like you to think about the test that we've been using and how we could apply it here to classify these points. So take about a minute and a half. See what you can sort of link up and write down whether you think these are local maxes or mins on the original function. Okay, so the way that we want to approach this is we want to think about the sign of the first derivative around the critical point. So when we read a graph, we go from left to right. And so when we look at the critical point, we want to label whether the first derivative is positive or negative to the left and the right. And as a reminder, a function will be positive if it's above the x-axis and negative if it's below. So if we go ahead and label near each of these points, we are able to see how they change. So at 0, our function goes from positive to negative, from above to below. If it goes from positive to negative, we have a local maximum. Here at 3.1, we see we go from negative to positive as we move from left to right. If we go from negative to positive, we have a local minimum. And then at 6.2, again, we go from positive to negative, which means that one is a local maximum. Okay, so if you are given a graph of the first derivative, this is the type of analysis you are doing to talk about the critical points and local maxes and mins of the original function. Okay, we want to extend this to the example we did with the table. Think about how we might apply it if we have data. So again, we looked at this table last class and we identified where the critical points are. So what we want to do now is think about where those critical points are going to be maximums or minimums. How can we use this first derivative table to help us determine that? So first, try to remind yourself of where the critical points are. There's 2 of them on this table. One straightforward, one a little bit trickier. And then once you remember where the critical points are, think about how we use the sign of the first derivative to determine if they're local maxes or mins. Okay, so take another just minute and a half. See if you can link up that test with this table to do this type of analysis. Okay, so let's start by talking about the critical points. So we know that our function will have critical points when the first derivative equals 0. We see that this happens at x equals 6. We have a first derivative value of 0. We also talked about last time that we're going to have another critical point between x equals 10 and x equals 12. And the reason we were able to figure that out is because this function is continuous. In order for the value to go from negative to, or from +2 to -1, it would have to cross through the axis, giving a 0 value somewhere between 10 and 12, right? So there's 2 critical points here, one at 6, one between 10 and 12. So let's talk about x equals 6 first. What we need to determine is the sign of the first derivative to the left and to the right of our critical point. So we see here that we are negative before our critical point and positive afterwards. So if our first derivative changes from negative to positive around a critical point, that makes the critical point a local minimum. Okay. Similarly, we see that we start off positive at 10 and we're negative at 12. If we change from positive to negative, that makes the critical point in here a local maximum. Okay, so again, because we know the direction they're changing, negative to positive or positive to minimum, positive to negative or negative to positive, that is how we link it up to the test to determine if they're local minimums or maximums. So in the case of the graph and in the case of the table, this is the only test we would be able to use to determine if they are local maxes and mins, because the only information we have is about the derivative, and we don't have a way of getting information about the original function or the second derivative based on this limited information. So we would have to use the second test in this scenario. Whereas we saw with the algebraic functions, we could use the original function to graph it, or we could use the number line to use the first derivative test. Okay, so as I mentioned, there are 3 tests. And so now we're going to talk about the third test in classifying critical points. So we started off with the original function, then we did the first derivative test. And so this third test we're going to use is called the second derivative test. Okay, and so I want to remind you that the way that we link up the second derivative to the original function, and again, this is back from chapter 2, 2.4 specifically, is that we know the sign of the second derivative tells us about the concavity of the original function. And so if we know the concavity and we know how it bends, that will give us the same information about whether it's a max or a min as when we visually look at the original function, right? Because if something is concave up, it bends upwards and it creates a minimum. And if something is concave down, it creates this maximum. Okay, so let's look at how this works. So we have the function that we started with for our other tests. We found the critical points by going through the first derivative. So we have 12x squared minus 12x minus 72. We factored that. We had x minus 3, x plus 2. We set that equal to 0, and that gave us our critical points of x equals 3 and x equals -2. Okay, so we graphed it with the original test. We did a number line with the first derivative test. So how would we use the second derivative to classify these critical points, right? So what we're going to do is we're going to start by finding the second derivative of our function. And we want to take the unfactored version to find the second derivative so that you don't have to do product rules when you don't need to. So here the 2 will come down to multiply the 12. We get 24x. The derivative of 12x is 12, and the derivative of 72 is 0. So the way the second derivative test works is that we are going to plug in our critical points. So we start by plugging in, we'll do the 3 first. It does not matter which order you do this. So 24 times 3 minus 12, and we're going to get a number, okay? So we crunch this number and we get 60. I'm writing the positive in front of it because what we're actually looking for is whether or not the number is positive or negative. So since we are positive at 3, that tells me that the original function is going to be concave up, Okay, so remember, if the second derivative is positive, the original function is concave up. Positive. Okay, if it's concave up, that tells me that my critical point is a local minimum. Okay, I can also do this with my other critical point. So I go ahead and I plug in a -2. And when I do that, I get -60. So since it's negative, if the second derivative is negative, the original function is concave down. Looks like a frown. You can draw a little face if it helps you remember, right? But we can see that that creates a hill, which means that -2 is a local maximum. And again, this will agree with the other tests we have done. We got the same conclusion, but we are able to, again, use the concavity to help us understand. So the test, the bullet points we can add to our test here is if the second derivative is positive at a critical point, the original function is concave up, and therefore our critical point is a local minimum. If the second derivative is negative at a critical point, the original function is concave down, and that gives us a local maximum. Okay, so now we're going to practice doing the second derivative test. And we're going to, again, use some examples that we've already found the critical points for. I will remind you what we got for critical points, but you are still going to have to find the first derivative to get to the second derivative. So for example, 1, our critical point was x equals -1. For example, 2, our critical points were x equals 3 and x equals -2. So what I would like you to do for both of these is I'm going to give you about 3 minutes. I want you to find the first derivative and then the second derivative using our derivative techniques. Then you're going to plug your critical point into the second derivative and determine whether the second derivative is positive or negative. Once you know that, you can use our statements to classify these points as local maxes and mins. If you still have time after you've done that, you can make sure that that agrees with the other 2 tests that we use to classify critical points, these same critical points in earlier problems. Okay, so take about 3 minutes, try that out, and then we will go through it together. Okay, take about 30 more seconds. All right. So as you can probably see, the value of the second derivative test is that when we already have to take the first derivative in order to find the critical points, if it is easy to then just take the second derivative, then we can get a lot of useful information without having to spend a lot of time futzing with graphs or drawing number lines. So you sort of have to make a decision about how complicated the second derivative will be to determine whether or not it's a good idea to use that particular test, right? When you have the option. So here, our first derivative is going to be 6x plus 6. We set that equal to 0. We find our critical point of -1. So when using the second derivative test, we now need to find the derivative of this. So something really interesting happens. The derivative of 6x is 6, and the derivative of 6 is 0. So there is no x to plug our critical point into. However, that doesn't mean we can't use the test. What this means is that the function has a second derivative that's positive everywhere, which means the original function is concave up everywhere, okay, including at the critical point. So if we are concave up everywhere, that means our critical point has to be a local minimum. So if you get a value for the second derivative instead of a function, you can still use that to classify your critical point. And if you remember, you may or may not, right? Our function, when we graphed it, looks like this. So we already kind of knew that it's just concave up everywhere and that our critical point is right here at -1. So this all agrees with what we've been doing before, okay? When we look at our next one, 6x squared minus 6x minus 36, and then we go ahead and take the second derivative, we get 12x minus 6. It's a pretty straightforward function, easy to work with. So then we can plug in our critical points without too much hassle. Again, it doesn't matter which one you plug in first or second, the order doesn't matter, you just have to do both of them. So we have 12 times 3 minus 6 here. That's going to give me 36 minus 6, which gives me 30. That's positive. If my second derivative is positive, my original function's concave up, which makes my critical point a local minimum. Okay, and then I also want to plug in my other critical point of -2. So again, I plug that right into my second derivative. When I crunch that number, I get -30. If your second derivative is negative, the original function's concave down, and you have a local maximum. Okay, so we are able to use the second derivative to classify those particular points. Now, I'm going to skip ahead because I want to make sure I get to the analytical example, but the next two are similar. You're going to do the algebra. However, for these two, the second derivative is not easy. It's actually pretty long and complicated. And I would say, sort of in the context of everything, I probably would not use the second derivative test to classify these, especially since we were able to do it with the first two tests we used. So it's up to you whether you want to try those two or not, but I want to make sure we get to example 5. So example 5 helps us tie together a lot of the things we've been looking at in this chapter. So here we have a list of information about different points on our function. F of x is continuous, it's differentiable, and we know these particular things about the function. So these are about f of x, the next 4 are about the derivative, and then the last 2 are about the second derivative. And the question is, determine where f of x is likely to have a local maximum or a local minimum. So I'd like you to think about this. I'd like you to take a good earnest look at this, and I'll give you 2 minutes so we have enough time to go through it. See what you can think about in terms of everything we've learned in this section, where those might be, local max and mins, and if we have the ability to classify them, go ahead and try and see what you can figure out. If you can't figure it out, that's okay. We'll go through it together. If you're able to figure it out quickly, you can try example 6, which is what conditions have to be true about A to have a local minimum, which is another analytical question that's trying to bring together the big picture. So try it out, take 2 minutes, we'll go through it together, and hopefully it'll help tie some of these ideas all together. Okay, take about 30 more seconds. All right, so I've sort of broken it down to the information we have by type. We have information about f of x, f prime of x, and f double prime of x. In order to even begin thinking about where we have local maximums and minimums, we need to think about where the critical points are. So critical points happen when the first derivative equals 0. So we go to the first derivative information, and we see that that happens when x equals 4, and also when x equals 9. So there's 2 places that we have critical points. So those are the places where we could potentially have local maximums and minimums. There's not any other information in the first derivative that would indicate anywhere else that we might have a critical point. So we can't use the f of x test because we don't have a graph and we don't have information about where it's increasing and decreasing. We could try the first derivative test, but I'm going to point out that we don't have any information about what's happening between 4 and 9. And that's one of the intervals that we would need to know. So that means we have to rely on the second derivative information. And that's where the second derivative is going to help us, this test, to classify these points. So the second derivative at 4, which is our first critical point, is -4. If the second derivative is negative, that means the original function's concave down, and x equals 4 is a local max. We also have information about the second derivative at 9. So if the second derivative at 9 is positive, so it's 3, that means that the original function is concave up. So that tells me that x equals 9 is a local minimum. Okay, so I was able to use the first derivative to find the critical points and the second derivative to classify them. Okay, so again, if you're interested in the solution to the 2 examples we skipped, 3 and 4, or example 6, you can check those out on the video linked in Moodle. Otherwise, we are good to go on this. And so I hope you have a great weekend, and I will see you next week on Tuesday.